All right, so let's wrap this all up. If we are working with a significance level of alpha equals 0.05, again, an arbitrary choice, but a conventional one, here we have a p-value of 0.021. We note that this p-value is less than our given alpha, so we would reject the null. Using the flowchart, the null was not the claim, and we rejected the null. We can restate this as the sample evidence support the claim that anxiety levels are different for the two testing situations. One of the last items we need to discuss is the calculation of Cohen's effect size for two sample t-tests. Now the formula is given as the difference in the means divided by the pooled standard deviation. It's technically the difference in the means less the hypothesized difference of the means, but if we're assuming those means are equal, that difference is almost always zero. So we can essentially just take the difference of the means as the numerator. Unfortunately, a lot of statistical software packages do not report the effect size, though this Excel template provided does include the calculation for this. This is one of the reasons why it may be important to know how to calculate the pooled standard deviation or the pooled variance from the output that you've actually been provided. Again, the effect size is meant to be a context-independent measure of how far apart the observed data is, either from each other or from some given fixed point. For our example, this difference in means would be classified as moderate. Again, we noticed that in this case, the effect size is given as the difference in means divided by the pooled standard deviation, which is calculated here in cell E27. The difference of the means comes from cell E5. The pooled standard deviation is the square root of the pooled variance, which is reported in cell E20. So an effect size of 0.76 is just short of 0.8, so again, that would be classified as moderate, but just on the verge of large. Note that the formula for effect size divides by the pooled standard deviation, whereas the t-ratio divides by the estimated standard error. But it turns out that the last formula, which uses the standard error, that standard error can actually be written as the pooled standard deviation times the square root of the sum of 1 over each of the sample sizes. Thus, if you only have the t-ratio and the sample sizes, which usually is part of the minimum requirement to be reported in any reputable peer-reviewed journal, you can calculate the effect size using this formula. The effect size for D is the t-ratio times the square root of the sum over 1 of each of the sample sizes. Before we proceed, there's one thing worth exploring. What factors make the t-ratio get bigger? Of course, the t-ratio is a fraction, and fractions get bigger if the numerator gets bigger or if the denominator gets smaller. So the three things that will make the t-ratio get bigger are if either 1, the difference in group means is bigger, 2, the pooled standard deviation gets smaller, or 3, if the sample sizes get bigger. Now it's important to note that the first two affect the effect size, but the sample size is not part of the effect size calculation, so it actually has no impact on the effect size. The next thing to address is the assumptions for the two independent sample t-test. There are three assumptions. The first is that the data should be normally distributed. The second is that the data should be independent, both within the groups and between the groups. And third, the population variance of the two groups should be the same, which means the standard deviations would be the same. This has a special name in statistics, homoscedasticity, 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 a fancy way of saying that the spread of the two groups are the same. Why are these assumptions important? Well, if these assumptions are met, then we can use the t-test that we just demonstrated to calculate a p-value. But what do we do if they aren't met? Well, if the data isn't independent, then kind of all bets are pretty much off unless we can spin an argument that using probabilistic analysis will still make sense. There are ways to deal with specific types of lack of independence, but we can't really cover them here. But if the data isn't normal, it turns out things really aren't that bad. Definitely not for larger sample sizes. And if the variability of the groups are different, then we can do a slightly different but closely related type of t-test. We'll come back and talk about the other t-test that's possible at the end of the video.